The fourth talk will be by Sebastian Musslick, now at Brown University. Sebastian.
Oh, can you hear me? Yeah, perfect. Yeah, I'm particularly excited to present my thesis work here since Coxa has actually been my favorite conference since grad school, so it's a particular honor. I want to begin my talk by acknowledging the human brain as probably one of the most complex intelligent systems on Earth that gives rise to many faculties such as language, creativity, and problem solving. And one could argue that our proficiency in any of those faculties is heavily reliant on our ability to coordinate information processing inside the brain. And that is something that we collectively refer to as cognitive control, which can be defined as our ability to guide information processing towards relevant tasks. But despite the capacity that the brain holds for cognitive control, we need to acknowledge that it is fundamentally limited. And these limitations, they carry enormous theoretical weight in cognitive science more generally. For instance, our limitation to execute multiple tasks, operations in parallel, is a fundamental premise of bounded optimality as a paradigm of AI, and also general theories of cognition that seek to rationalize human behavior within the constraints, adaptations to these constraints in the cognitive architecture. And so the core of my thesis is to kind of explain why do we have those limitations in the first place, and to develop methods for the quantification and navigation of these limitations in the human brain. And as I will explain in a second, cognitive psychologists have actually tried to address this question for almost a century, but without considering the processing characteristics of the human brain. And so a cornerstone of my approach is to consider these limitations within the neural architectures, the processing characteristics of neural systems. And as I will show, this approach allows us to combine insights, empirical and theoretical, from machine learning and neuroscience, and provide novel insights and formal grounding to old premises in cognitive psychology. And the prevailing view is actually that these limitations can be attributed to structural or metabolic constraints of a centralized control system. And this traces back to possibly one of the first theories of modern cognitive psychology that poses that there is a central bottleneck that can only execute one task at a time. And this theory has been so influential that it contributed to the notion that cognitive control relies on a central capacity limit processor. And according to that control reflects a constraint that is a bound on rational processing. But what these theories do not explain is why, for instance, these constraints would specifically apply to control-demanding tasks. Given that we have billions of neurons all available for parallel processing, and given that there are similarly demanding tasks occurring at the same time, like, for instance, face recognition. And so what I wanted to do in this thesis is kind of challenge the fundamental premise that there is a central capacity constraint on the control system itself, and instead build on the idea that these limitations might reflect rational solutions to fundamental computational dilemmas in neural architecture. And so in this talk, I would like to focus on the first chapter of my thesis, which pertains to the trade-off between shared representations for learning efficiency on the one hand, and separate representations for multitasking capability on the other hand. In the former case, these shared representations, they pose a risk of conflict, and we need cognitive control to adjudicate that conflict. Whereas in the latter case, there is no conflict, and thus no need for cognitive control. And note that this dilemma view kind of inverts the standard interpretation that control reflects a bound on rational processing. Instead, here, one could argue that control reflects a rational bound on processing, that is a rational response to the dilemma posed by shared representations. And to illustrate the effect of shared representations, I would like to perform an experiment with you. And in this experiment, I'm going to ask you to name the color of the following stimulus on the screen out loud, and at the same time point to where it is on the screen. So I'm going to give you an example. Here you're supposed to say yellow out loud, and at the same time point to the right side of the screen. Okay, ready? Okay, so you quickly were able to do this task in this multitasking condition and performed really well. Now I'm going to teach you a new task. In this new task, you don't have to say anything out loud. You're just supposed to point. And you're supposed to point left if the word says red, and point right if the word says green. You can ignore the color of the stimulus, just respond to the word. So if it's the word red, point left. If it's the word green, point right. So just to give you an example again. Yeah, you're supposed to point to left. Okay, ready? Okay, so you're all able to do this task, and now I'm going to do ask you to multitask again and perform the exact same task you just did. That is, if the word says red, point left. If the word says green, point right. But at the same time, name the color of the stimulus out loud. Okay, ready? Okay. So you might have experienced the same thing that Princeton undergrads did, which is that they performed really well in this first multitasking conditions, where they had to name colors and point to the location of the stimulus. They're also able to acquire this new task fairly quickly that requires mapping, basically words onto locations on the screen, but somehow, did really badly in this last multitasking conditions. And so, to explain why we perform well in some multitasking conditions but not others, I want to introduce you to a really simple neural network model of controlled processing that has an input layer that encodes stimulus dimensions like color, word, and locations, with each unit corresponding to an individual feature like a particular color. And it passes this information to an internal associative layer that represents the stimulus up to a response layer at which the network can indicate a response either verbally or manually. And with the setup, you can essentially formalize tasks as mappings between these inputs and outputs. So for instance, the color naming task would be a mapping between colors and verbal responses. But with the system as it is, there is a lot of stuff going on. There's a lot of interference. For instance, the verbal response layer now receives input from two different sources, from colors and words, and what if they disagree? So, and you can see that this red pathway, for instance, maps words to verbal responses, and that is what we know as word reading. And so in order to execute one task, we need some kind of system that allows us to control information flow in the network. And so we want to introduce a control system that biases information and flow in the network by engaging the representations for the relevant tasks and deactivating representations for the irrelevant tasks. So in the case of color naming, this would amount to activating representations for colors in the associative layer and the representation for verbal responses in the output layer. And with the system, I can also perform two tasks at the same time, like color naming, mapping colors to verbal responses, and pointing to the location of the stimulus by mapping locations onto many responses. And I can do so by engaging representations for colors and locations in the associative layer and verbal and manual responses in the output layer. But this doesn't always work so well. For instance, in the last multitasking condition of the experiment, we were asked to map colors onto verbal responses and at the same time point to what the word indicates. And you can see to perform those tasks, you need to essentially engage the color and word representations in the associative layer and the verbal and manual response representations in the output layer. And doing so engages the third processing pathway that interferes with the color naming task. So you can see that there is now interference, and this interference occurs in two places. First, the verbal response layer now receives input from two different sources again, colors and words. But the reason for this interference to occur in the first place is a shared representations between the pathway that maps words onto manual responses and words onto verbal responses that we know as word reading. And so if we want to execute one of those tasks, mapping words onto manual responses, we need to engage that representation for words. But doing so allows information to leak through onto the color naming pathway. And so the key takeaway here is that the limitations in multitasking in this example are not the result of a central limitation of a control system. They're the result of these shared representations. And one could even argue that it is the very purpose of control to avoid such interference by limiting processing to a single task. Now, one could argue, okay, well, this is a particular example, but what if I wired up this network in a different way? What if I allocated a separate processing pathway from words onto manual responses such that I can avoid this multitasking interference? And while this solution would work, your evidence, the empirical observation that you weren't capable of performing this multitask is evidence that this is not probably what's going on. So the key takeaway from this example is that these shared representations impose limitations on control-dependent processing and multitasking, which is an expression of multiple resource theory. But this example also leaves two important questions unanswered. First of all, do these detrimental effects of shared representations prevail in a system as large as the human brain? And assuming they do, why do we want to share representations in the first place? And so to answer the first question, we kind of abstracted away from these complicated neural networks and considered essentially neural systems as graphs. And we asked, how does the multitasking capacity of such a graph scale as we increase the amount of representation sharing, here operationalized as the number of edges that shares a single processing node. And doing this and several other analyses, we observed that the multitasking capacity of a system, that's here shown on the y-axis, decreases drastically with the amount of representation sharing in the system. And interestingly, it doesn't necessarily help to make the brain bigger, to increase the structural capacity of the system, because as long as there's some amount of representation sharing, the multitasking capacity drops. And what we could also show is that through functional analyses, is that the amount of representation, the detrimental effect of representation sharing is actually amplified by the amount of interference that it transmits, but also by the degree of persistence, the degree to which these shared representations persist over time in a neural system, activities being carried over. And using some neural network simulations, we were able to show that these three factors in neural systems are sufficient to account for a variety of cognitive control phenomena that have been largely considered in isolation for the past century. So if these shared representations are so bad for processing, one could ask, well, why do we want to have them in the first place? And so actually, Kelsey actually spoke to that question in her talk earlier. In machine learning, these shared representations are considered very beneficial for learning and generalization as they promote that. And what we could show in collaboration with a former Glushko Prize winner, Andrew Sachs, we could show that at least for linear neural networks, learning efficiency, the square of learning efficiency is essentially proportional to the desired amount of tasks that we can execute at the same time. And this exposes a fundamental trade-off between learning and multitasking. And one can also show that it is indeed optimal for a neural system in many situations to rely on these shared representations for the purpose of learning efficiency, especially if the agent has very little time to perform the tasks. And so this suggests that these limitations in multitasking capability and cognitive control may reflect a preference of a neural system to rely on shared representations as opposed to separate representations. But if a system cannot execute multiple tasks simultaneously, then the only way to multitask is to flexibly switch between different tasks. But this imposes another dilemma, which is the stability-flexibility trade-off. The idea is that the more you focus on a single task, the more you kind of isolate and make this representation robust against others, and the harder it is then to switch and flexibly reconfigure the system and switch to another task. And so by formalizing this trade-off in dynamical systems, we could actually show that actually it is optimal for neural systems and also humans to impose a limitation on the amount of control that is allocated just to a single task, to essentially make the system more flexible, especially in these kind of environments that demand flexibility. And so with that, one can summarize that these limitations may provide a lens through these general capacity limitations in terms of these fundamental computational dilemmas, may explain why it is in fact rational to be limited, both in terms of multitasking and in terms of the amount of focus to a single task. And you can really consider these computational dilemmas as fundamental principles of computation that may also apply to artificial systems that then need to solve these kind of problems, especially as they become increasingly similar in terms of the processing characteristics as the human brain. And so with that, I would like to thank you for your attention and also first and foremost my PhD advisor, Jonathan Cohen, various collaborators at Princeton and other academic institutions and industry, and thanks again for your attention.
Questions for Sebastian? There's one online that I'll read while people have a chance to come to the mic. Would you consider the problem of multitasking analogical to the problem with falsely combining features from different objects? And we can solve the problem by introducing an attentional bottleneck to process each object sequentially. So is multitasking like the challenge with objects where we just have to process them separately?
I'm really curious who asked that question. Yes, absolutely. I think that these fundamental computational dilemmas of representation sharing and separation also equally apply to limitations in other systems. That includes working memory, for instance, but it also includes, as the person asked, visual attention. So for instance, if visual features are shared between objects, then the only way to solve the binding problem is to essentially focus on one object at a time, because otherwise what would happen is that there would be crosstalk between the different features of the different objects. It was in fact, Friesman and Gary Gillard in the 80s already suggested that it is a fundamental purpose of visual attention to be limited in serial just to exactly solve this feature binding problem, although they didn't hint at the origin of the problem, which is that the features might be shared. And you can actually, if some of you are familiar with DALL-E, this new image processing engine, that also is kind of trained based on shared representations, you will see that if you ask it to produce pictures of two different objects, you will often see that the features of those objects often confound it. So in fact, the AI exposing exactly that feature binding problem because it relies on these shared representations, and the solution would be to implement a serial visual attention bottleneck to solve that problem, according to Friesman. Yeah.
Yeah, great talk. In my experience, it is often very hard to distinguish shared representations from shared processes. You didn't seem to have time to go into that very much, but maybe you'd like to say a few words.
Yeah, it's a really good question. This problem has been partly addressed by, I know, Jim Townsend and colleagues, where the question is, for instance, to what extent can you say if a system is actually operating in serial versus parallel? And it's really hard to tell the difference, and one approach to doing so is to look at reaction time distributions. And you can make certain predictions under the assumptions that processes are actually operating in serial versus in parallel, because you can formulate bounds on the reaction time distributions, assuming they do. What we can actually show is that if representations are shared, then processes, the optimal way to execute tasks is to indeed serialize, and that actually conforms with the reaction time distributions that were proposed by Townsend and colleagues, where you can indeed show that it is optimal to serialize if representations are shared.
The final talk of this session will be